Our learning objective is to analyze and graph rational functions. So what is a rational function? A rational function f of x is a quotient of two polynomial functions a of x and b of x, where the function b is non-zero. Using mathematical notation, this means that the rational function f of x is equal to a of x, which is a polynomial, over b of x, which is another polynomial. And then we have the condition that b of x, which is the polynomial in the denominator, cannot equal 0. If it does equal 0, then f of x is undefined. So the domain, which is the x values of a rational function, is a set of all real numbers excluding those values for which b of x equals 0, otherwise known as the zeros of b of x. Now that we understand what a rational function is, how do we actually graph this rational function? Well, we'll use the following 4 steps, which I will explain further in the examples in this video. So we have step 1, find the domain. Step 2, find any asymptotes. Step 3, find the intercepts. Step 4, find and plot values in the test intervals and then graph. So 2 important things we need to understand before I go through the examples in this video. N equals the degree of the polynomial a of x, and m equals the degree of the polynomial b of x. So n is the degree of the numerator, m equals the degree of the denominator. In example 1, the degree of the numerator is less than the degree of the denominator. So we can see here that the degree of the numerator, n equals 0, and the degree of the denominator, m equals 1. So in this example, for the function g of x, we're asked to determine any vertical and horizontal asymptotes and intercepts, then graph the function and state its domain. So now if you look at g of x, we can see this is already simplified. We can't factorize the top or the bottom, which means we can go on to step 1, which is to find the domain. And we do this by setting the denominator equal to 0. And when we solve this, we get x equals minus 3. So this tells us for the domain, x is all of the real numbers, but it excludes minus 3. The second step is to find the asymptotes. So now because x cannot equal minus 3 in the domain, we have a vertical asymptote at x equals minus 3. And since the degree of the numerator is less than the degree of the denominator, we have these 3 conditions here. And we can see this one satisfies the first one. So this tells us that the horizontal asymptote is y equals 0. So we have the 2 asymptotes we're looking for. So moving on to step 3, which is to find the intercepts. We start off with the y-intercept. What we do is substitute x equals 0 into this function here, and we'll get this, a value of 2. So our y-intercept has coordinates 0, 2. For the x-intercept, we make the numerator equal to 0. Now we know this doesn't make sense. 6 cannot equal 0. Therefore, we don't have any x-intercepts. And then the final step, step 4, is to graph, which I'll show you on the next slide. So in step 4, we'll graph this information that we found in the previous slide. So we have a vertical asymptote at x equals minus 3, which goes here. And we have a horizontal asymptote at y equals 0, which goes along here. And then there's a y-intercept at 0, 2, which goes over here. So now that I've plotted my asymptotes and my y-intercept, I'm going to produce a table of values. And in the first column, we have what we call test intervals. So our first interval here is between negative infinity to negative 3. And our second test interval is between negative 3 to positive infinity. And what we want is 2 to 3 points in this test interval and 2 to 3 points in this test interval. So I've picked these x values here. Now you can pick more x values for more accuracy. However, this will become time consuming, but with practice you'll get better at picking less x values. So now that I have my x values, I'm going to substitute them into this function over here, which will give me my y values, and that will produce me my set of coordinates like this. And with our set of coordinates, we can then plot these onto this graph over here. So the first one will go there, the next one will go over here, and the next one will go over here. And then in our second test interval, we have the first point going up here and our final point going over here. And then we join them up with a nice smooth curve going through all our points, like so. Okay, and then one down here or up here in this test interval, like so. And then going back to our original question, it says determine any vertical and horizontal asymptotes which I have over here, and any intercepts which I have over here. Then it says graph the function which I have, and state its domain, which I have already done as well, and that completes the question. So now in example 2, we have the degree of the numerator being equal to the degree of the denominator. And the first thing we're going to do is to find any common factors and simplify where possible. So if I look at the numerator here, I can take a factor of 3 out, which will give me x squared minus 1 in brackets, all over, and then we look at the denominator here. This is a difference of 2 squares, which I can rewrite as x minus 3 and x plus 3. Now if we look at the numerator over here, x squared minus 1 is another difference of 2 squares, so I can use that technique to factorize further. So we will have in the numerator 3x minus 1 and then x plus 1, and the denominator will remain the same. So this shows us there are no common factors. F of x is as simplified as it can get. So now we can move on to step 1, which is finding the domain. And as previous example, we set the denominator equal to 0, so we'll get the values x equals 3 and x equals minus 3, which makes the denominator 0. So this tells us that for the domain, x is all of the real numbers, but excludes minus 3 and 3. So our second step is to find the asymptotes. So because the domain excludes x equals minus 3 and x equals 3, we know that these vertical asymptotes are x equals minus 3 and x equals 3. For the horizontal asymptote, we know that the degree of the numerator, n equals 2, and the degree of the denominator, m equals 2. So they're the same. So n equals m. Then we have these three conditions here, and this here satisfies the second condition. So this tells us the horizontal asymptote is y equals a sub n over b sub m. Now, a sub n is the leading coefficient of the numerator, which is 3, so I'll write that down here, over bm. And this is the leading coefficient of the denominator, so we can see that's 1. And 3 over 1 will simplify to give us 3, so we have a horizontal asymptote y equals 3. So we'll move on to finding the intercepts in step 3. So for the y-intercept, we substitute x equals 0 into this function here, and when we do that, this will simplify to give us 1 over 3. So we have a y-intercept at 0 and 1 over 3. For the x-intercept, we make the numerator equal to 0. And if we do that and solve, we get the values x equals minus 1 and x equals 1. So this tells us we have x-intercepts at minus 1, 0 and 1, 0. And then the fourth step is to graph, which we'll show you on the next slide. So in step 4, we graph the information that we've found over here. So we have a vertical asymptote at x equals minus 3, and another one at x equals 3, a horizontal asymptote at y equals 3, a y-intercept at 0, 1 over 3, x-intercept at minus 1, 0, and another one at 1, 0. So now that we've plotted our asymptotes and our intercepts, we've reduced a table of values like this, and we can see there's 3 test intervals. So they go from between negative infinity to negative 3, then negative 3 to positive 3, and then from positive 3 to positive infinity. So now we want to find 2 to 3 points in each test interval. And the x values I've selected are here. We substitute these x values into the function f of x to give us a set of coordinates like this. So the first 3 points goes in the first test interval, like so. And then we have 2 points going in the second test interval here and there. And then we have the final 3 points going in the third interval, which goes here, there, and the final one over here. And then we join them up with a nice smooth curve going through each point, like so. And in the second test interval, you can see the graph goes up and it comes back down again. So these 2 points that we used was important to help us find out the shape of the graph. And then we have the final part of the curve going like so. Then if we look at the original question, we found the vertical and horizontal asymptotes over here, we found the intercepts over here, and we've graphed the function over here, and we've stated the domain earlier on in the question over here.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom, where we cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. The first session is always free. So if you are interested in a free lesson, click the link in the description below. To book a lesson, you can always send us a direct message on Instagram at Mr. Mathematics. Okay, with that said, let's get back to our lesson.
In example 3, this time, the degree of the numerator is bigger than the degree of the denominator. And then we have this function f of x, which we'll try and find common factors for and simplify. So we can see for the numerator, this doesn't factorize. In the denominator, we have a quadratic, which we can factorize to give us x plus 4 and x minus 3 in brackets. Now we can see there's no common factors, so this is as simplified as it can get. Okay, and then we can move on to step 1, which is finding the domain. So what we do firstly is set the denominator equal to 0. And if we do that, we'll get the values x equals minus 4 and x equals positive 3. So this tells us for the domain, x is all of the real numbers, excluding x equals minus 4 and x equals 3. So for step 2, we'll find the asymptotes. So here in the domain, x equals minus 4 and x equals 3 is excluded. So this tells us there's vertical asymptotes at x equals minus 4 and x equals 3. And then we know the degree of the numerator, n equals 3, and the degree of the denominator, m equals 2. So this tells us that the degree of the numerator is bigger than the degree of the denominator. And then we have this set of conditions here for the horizontal asymptote, and this satisfies the bottom one. So there is, in fact, no horizontal asymptote. Now what we'll notice is that the degree of the numerator is 1 more than the degree of the denominator. So I can rewrite n as n equals n plus 1. So this just tells us that the degree of the numerator is equal to 1 more than the degree of the denominator. Now if we have such a case, what we need to do is use polynomial division. And we use this on the original function. So when we use polynomial division, we end up with rewriting it like this. And then the first part we have over here is the function for what we call an oblique asymptote. Now, an oblique asymptote is neither vertical nor horizontal. Okay, it's a diagonal line. And the equation for the oblique asymptote is y equals 2x minus 2. And we get that from here. So now that we found the asymptotes, we move on to step 3, finding the intercepts. So we'll start off with the y-intercept, and we do this by substituting x equals 0 into this function here. If we do that, we end up with a value of 0. So our y-intercept is at 0, 0, which is going through the origin. And then for the x-intercept, we make the numerator equal to 0, and if we solve, we get x equals 0. So the x-intercept is at 0, 0. Now again, these are the same points, so actually we don't have a separate x or y-intercept. We just have one intercept at 0, 0, which is the origin. And then step 4, we'll graph, which we'll show you on the next slide. So for step 4, we graph this information that we found on the previous slide onto this grid here. Now, we've had to condense this grid because the values that we end up with from this function are quite large. So what we need to do is be extra careful and try to be as accurate as possible when plotting. So we have a vertical asymptote at x equals minus 4, another one at x equals 3, an oblique asymptote at y equals 2x minus 2, and an intercept at the origin 0, 0. So we produce a table of values like so, and we have 3 test intervals. So we have between negative infinity to negative 4, and between negative 4 to positive 3, and then between positive 3 to positive infinity. Okay, and then we want some points in each of these intervals. So these are the x values that I've selected. We substitute these x values into this function f of x, and that'll help us produce a set of coordinates like this. Now you'll notice in the second test interval, I have actually 4 points there. And the reason I've done that is because I have 2 points over here, which is to the left of this origin, and 2 points over here, which is to the right of the origin. And what this will do is help us find the shape of the curve in this second test interval, or the correct shape of the curve in this second test interval. Now we can just plot these coordinates into our grid over here. So the first 3 points go over here, and the next 4 points go over here, and then the final 3 points go over here, and then we join them up with a nice smooth curve going through each point. So for the first test interval, you can see the graph goes like so, and then for the second test interval, we can see the graph goes through the origin and goes further downwards. So it could have gone upwards, but because we had these other 2 points, it helped us point us in the right direction, going downwards. And then for the third test interval, we can see the graph goes like so. And then if we look at the original question, we found the asymptotes and the intercepts over here. We've graphed the function over here, and we've stated the domain earlier on in the question, and that completes this question. So in example 4, we have a function which has common factors. So now what we'll do is we'll factorize the top to give us x minus 2 and x plus 2, and then we'll factorize the bottom to give us x minus 4 and x plus 2. These two will cancel each other out to give us a simplified function x minus 2 over x minus 4. Now for the domain, we set the denominator of the original function to 0. So we'll end up with x equals 4 and x equals minus 2. So this tells us that the x values are all of the real numbers excluding minus 2 and 4. Because this function has common factors that simplifies to give us this, we have to be careful with our excluded x values. So if we start off looking at x equals 4, this is what we call the real zero of the simplified denominator. So here is our simplified denominator. And then x equals minus 2. Well, if you look at this bracket, x plus 2, we can see it doesn't exist here. It got cancelled out earlier on. So what do we call x equals minus 2? Well, this is a removable discontinuity, or called a hole, and we represent it on the graph with this empty circle over here. Now, we have the x value for this hole. We need to find out what the y value is. So we substitute x equals minus 2 into this simplified function to give us 2 over 3. And we don't substitute it into the original one because it's undefined here. If we tried that on a calculator, we'd get a mathematical error. So step 2, we'll find the asymptotes. Now we have a vertical asymptote at x equals 4. Because at x equals minus 2, we have a hole. And for the horizontal asymptote, we know that the degree of the numerator, n equals 1, and the degree of the denominator, m equals 1. So they're the same. So because them two are equal, we can look at the second condition, and then to find out the horizontal asymptote, we write y equals the leading coefficient of the numerator, which is 1, over the leading coefficient of the denominator, which is also 1, and that'll simplify to give us 1. So for step 3, we find the intercepts, and then for the y-intercept, we substitute x equals 0 into the original function to give us a half. So we have a y-intercept at 0 and a half, and for the x-intercept, we make the simplified numerator equal to 0 to give us x equals 2, and then we have the x-intercept at 2, 0. So for step 4, we graph the information over here that we found. So we have a hole at minus 2, 2 over 3, vertical asymptote at x equals 4, a horizontal asymptote at y equals 1, and a y-intercept at 0 and a half, and an x-intercept at 2, 0. Then we produce a table of values like so. So we have 3 intervals, and they go from negative infinity to negative 2, from negative 2 to positive 4, and from positive 4 to positive infinity. So I choose my x values as this. I substitute these into this function h of x to give us these set of coordinates. So now that we have our set of coordinates, we can simply plot them in as follows. And then when we've done that, we can finally join them up with a nice smooth curve, like so. And then that's our completed graph. So here are 4 questions for you to practice yourself. I suggest you pause the video before I reveal the solutions. So here are the solutions for question 1 and 2, and the solutions for question 3 and 4. Thank you.